essentially my wife's fault. And I'll tell you why. So we got a kid, and then she said we needed a bigger car. So we went around and started looking for cars. And then she said we needed leather seats. And then because it's easy to wash if something happens with the baby. So I said, well, okay, let's get some cars. Let's get to see some cars. So we saw some cars, and we bought a car where they told us, well, if you want leather seats, then it comes only in the package, and this package also has these passive keyless entry and start systems. So about a year and a half ago, we got the car. I have no clue what these systems are, and then I started looking at these systems. So how does this system work? Well, just to give you an overall idea of what this talk is about, I keep my key in my pocket. I approach my car now knows that I'm close to the key somehow close, and it will unlock, which is very convenient if you're holding a baby in one hand and a couple of bags in the other hand. It really helps that your car unlocks. You don't have to look for your key or in your purse or whatever. Also, if you enter the car, your car will somehow detect that you're in the car, which means that then it will just simply light up a little button, and you will be able to press it and start the car. So it's very convenient. It's all about convenience, and it's currently being deployed by all major car manufacturers. Some of the car manufacturers have it deployed in the next generations as a default. You're no longer going to be able to buy a car with a different kind of a key. So this is a type of a car key which is going to be pervasively used all around. It already is used quite extensively. So what is this all about? Well, I will give you an overview of car key systems, how car key systems developed in the past, some previous attacks on these systems. Then I will introduce this passive keyless entry and start system, and I said the latest convenience system that we have. And then I'll show you how easy it is to steal such cars. So not only to open the cars and to enter into these cars, but also to steal these cars in the right way. Okay? And it's extremely easy. All that you need is a piece of cable. Trust me, you'll see cars. I'll show you our analysis on 10 different car models. I'm not going to give you the names of these car manufacturers, but we haven't found a single car manufacturer that has a system that protects against these attacks, starting from cars that cost over 200,000 Swiss francs, which we tested because of some volunteers from Zurich area and other areas in Zurich, and to low-end cars. So all the cars are vulnerable to this kind of attack. And then I'll draw some conclusions on how this can be potentially fixed. And the fixes are actually not that easy. The fixes are pretty nasty. So I think it's not a surprise for everyone that the cars contain many components, many little computers running around, embedded systems that run around. And we have entertainment system, engine control systems, distance radars, onboard computers and networks, and we have even high pressure sensors that are connected wirelessly to the rest of the car. Now, in recent years in security research, especially in the applied security research, there were many attacks on these cars. So researchers showed that if you can get into the car, you can actually modify, you can connect to the main bus of the car and modify all kinds of settings, essentially bringing the driver into danger. People have also shown that you can remotely hack into these tire pressure sensors. So these tire pressure sensors are connected wirelessly to the rest of the car for many reasons. So they managed to hack into those and indicate false tire pressure information to the car, which can of course lead to all kinds of reactions of the car, because the car might think that the tire is deflated and then react in some unsafe manner. And of course there are keying systems that evolved over time. And what kind of keys did we have? Well, the metallic key doesn't require a lot of introduction, right? We don't know what the metallic key is. Then we learned over years that we can open cars remotely. So we take the key, we press a button, the car opens remotely. Then cars started, because of open theft, cars started having immobilizer chips to see how those work. And then finally, passive keyless entry start systems where you keep your key in your phone. So these are four categories of key systems, and each is somehow vulnerable. The metallic key, you know how secure it is. If someone makes a similar key, you are the system is pretty much broken. So in terms of active keys, so we know that you can press a button to open the car. Physical keys need to start the car. You need to be close, about 100 meters. There is a shared cryptographic key between the key and the car, and the biggest attacks essentially leverage on this on systems like weak cryptography. So there were attacks like attacks on key lock at various crypto conferences where they showed that these weak ciphers cannot be used because if an attacker observes the communication between the key and the car, they can actually retrieve the key and therefore open the car at any time they want. Then there are keys with immobilizer chips. It's essentially a small passive RFID device in the key. And if this RFID is present close to the lock, then the car will allow to be started. So this passive RFID authorizes the start of the engine. You need very close proximity, like centimeters, and this is present in most cars today that have metallic keys and that have remote open abilities. So again, there is a shared cryptographic key between the physical key and the car. And again, there were previously attacks on the crypto, which was implemented here. Now, weak crypto was used mainly for efficiency reasons, and for example, there are attacks on these systems which were presented using security prevention. So these systems were broken because of the weak crypto. Now, passive keyless entry and start systems. Well, you need to be close 2 meters to the car, and the car will allow you to open it. You need to be in the car to start the engine, so that the car will sense that you are in the car or that you are outside of the car. And there is no need for human action of the key. In all these other solutions, you have to somehow find your key and enable the car to start. So the system allows for the car to start in a convenient way. So what were the previous attacks in practice that thieves typically used? Well, there were protocol attacks. So if the crypto or the protocols were designed in a weak manner, then you could, for example, replay messages. For example, a lot of aftermarket systems that we tested essentially just always send the same ID between the key and the car. And of course, once that you eavesdrop on that ID, you can replay it and you can open the car at your will, right? So even if the messages are encrypted, they don't have freshness, which means that then you can just take the old messages, replay them, and the car will open. So which means that even if you use strong crypto and if you don't design your protocols correctly, these kind of attacks are feasible. So the requirement here is that you are able to eavesdrop the message and you have to have the ability to resend it. Now this is today with software-defined radios pretty easy to do. This can be reused without the presence of the car. Very good. So that's fine. Also other attacks that I guess you heard about were radio jamming attacks. So you know that your car will be unlocked when you exit your car. Now you have to press the button for your car to lock. So you would press the button for your car to lock. However, the attacker would jam this communication link and your car will never lock. So when you were leaving the parking lot, you believed that your car was closed, but in fact someone was jamming these messages and therefore the car never locked. Now this is also pretty easy. These are low power radio devices, which means that they're using low power for the transmission and it's very easy to jam. And the cars don't have any jamming detection capabilities and therefore this attack works. So so you might notice this, you might not notice this. That's why some cars beep when you close them, or they blink the indicator lights in order to make sure that the owners actually notice that something happened, that the car indeed closed. So this attack also doesn't allow you to start the car. So you can only just enter the car and steal whatever's inside, but you can't really start the car. Okay, we went over these crypto attacks. And recently what researchers started doing in cars is to have remote and attacks on the car software. Now the software deployed in the cars is becoming more and more complex. The cars have GSM and GPS receivers on them, And the attackers managed to show that you can actually remotely hack into those systems and open cars. It's not that easy. It doesn't work on all the systems. However, if for example someone gives you even a CD that you play in your car, this might actually enable an attack on your car. So you play a CD, it's a part of the entertainment system. However, this CD contains some binary which will be executed and will compromise your entertainment system, and then it will also this malware will spread into the main control systems of the car. So these attacks were recently shown as well at IEEE Security and Privacy Symposium. So the main topic of this was just to give you some background information about what's in the landscape of cars and more precisely of keys, how you open your car today. But I guess that's not a surprise. Now what I want to tell you is how passive keyless entry and start systems work. So these new systems that are deployed, and then how they can be easily attacked. So passive keyless entry and start systems have different modes of operation. So a normal mode of operation uses two radio channels. So there is when you come close to your car, the car will talk to you on one channel, to your key on one channel, which is essentially a magnetic coupling or inductive coupling channel. Right? So the car will excite the key, and then after that, the key will reply back on a UHF channel. So on a different channel which has a longer communication range. So we have two channels. And this is the normal mode of operation. This is the mode of operation in which you keep your key in your pocket, and this is best for your convenience. Of course, other modes of operation are supported, like active, that you actually press a button on your key, which is an active remote open mode, right, which is present in other types of keys. An interesting mode is also a battery depleted mode. Now you could think that your key, that your battery is down. Now the problem would be, how do you enter your car, right? Well, in this case, your key not only contains an active RFID tag, which will be used in the normal mode of operation, but it also contains a passive RFID tag. So if your key is completely deleted, this device will be a passive device, which you will have to put really close to the lock of the car, and then the car will unlock. And equally, when you enter the car, you would have to put it really, really close to the ignition button in order to have it start. So there is a sort of a backup solution if your battery is there. But the normal mode of operation is what we will focus on. So it uses two radio channels. When you come close to the car will challenge you on one channel, and the key will reply on a different channel. Okay. So how does it work? So again, you need to be close 2 meters to the car, and the car will open. You need to be in the car to start the engine. So there's no need for human action. So let's say that this is your key, and this is your key. It moves closer to the car will then unlock because it's in some range. There are actually antennas embedded in the doors of the car, which are larger antennas, and they will then push the signals towards the key. There are different types of systems here. Some cars will emit the radio waves all the time, and some will start emitting only if anyone just holds onto the handle, right? And then they will start transmitting. So when you come close, when your key is close in some range, the key will sense the messages from the car and will reply, and the car will unlock. Equally, when you get inside of the car will sense this. There are antennas embedded in the ceilings and in the front panel, and it will detect the keys inside, and then this little light will light, and you will be able to start the car. Now, here this feature was introduced because people were afraid of the following attack. What if I'm at a petrol station and now I step outside, I want to get some petrol, someone just enters my car and presses the button to start. So the key actually has to be in the car for the car to be started. Okay, now you can start your car. So the car will essentially issue periodic scans, as I said, on an LF channel, 120 to 125 kilohertz. This is 1 to 2 meters inductive coupling communication. And then the key, it will embed some sort of a fresh challenge. So the challenge will be fresh. There will be an acknowledgement of the proximity over a UFH channel. Then the car will issue a car ID and a challenge. This will be a fresh challenge on an LF channel. The key, the cryptographic key in this physical key that you call will compute some function over this challenge and will respond back with a freshly generated reply. So you have a perfectly valid challenge response protocol. Some of these keys even use AES, which means that it's very difficult to launch any attacks on the crypto, which is useful. So we have these two channels, LF 1 to 2 meters and UHF, which is 50 to 100 meters. So as we said, cryptographic keys provide authentication with challenge response. So replaying old signals will not be feasible. Timeouts, freshness is used, so there is no problem there. Car-to-key communication is inductive low frequency signals, so you would expect that no one who is outside of a close proximity of the car will be able to hear the messages from the car. And also the physical proximity here, this is the key problem that we detected, is detected by the reception of the messages. So if you go here, if you go back here, the notion that the owner of the key is in front of the car is asserted by the idea that only the valid key will be able to hear the message from the car. So, or more simply, the idea is that if the car and the key can communicate, therefore the owner is close. But this is completely bogus, right? If you know anything about wireless communication, you know that this is entirely bogus. So even if you use inductive coupling communication, this kind of an attack is perfectly feasible. So this is in a nutshell how our attack worked. We got within 8 meters from the, I'll show you the numbers later on, from the owner of the car who has the key. So you imagine you park your car in front of Cope, you go to Cope. Someone is standing at the door 8 meters away from you, holding a small antenna. Now this antenna and his partner is standing close to the car, right? Now the antenna close to the car will pick up the signals from the car. This is LF inductive coupling communication, but still you can extend the range up to 8 meters here. So you can pick up the signals from the car, you can amplify them, you can relay them to another antenna which will excite the key in someone's pocket, and then you can relay the signals back to the car, and the car will unlock. Now the same thing will work if you enter the car and if you sit in front of the ignition key, you will excite the key, and you will be able to prove to the car that you are in the car. So there is absolutely no problem to do this kind of relay attack. It costs 50 Swiss francs. You can stretch a piece of wire and put 2 loop antennas on each end. You can amplify the signal in between, maybe. You don't need it for some models. And you will open these kind of cars. And this was our first test. And we were really shocked that you can defeat such systems in such a simple manner. Let me give you another scenario that we tested. So we went to a house. We went in front of a house. The keys of the car were left on a kitchen table. Right? We came outside. Outside, we leaned against the window. We put our antenna, which was about this big, next to the window. We excited the key. The key was 3 meters away from our antenna. We excited the key. We pulled a piece of cable. And we excited the car with a different antenna. The car was in course parked in front of the house. We opened the car, we turned on the engine, and we left. Now the cool thing about this attack is that even when the relay is broken, you can continue driving. I mean, your car is not going to shut down because it cannot find the key anymore. Imagine you driving at 140 kilometers kilometers an hour on a highway and your kid throws your key outside of the window, your car shouldn't stop. That's a safety hazard. Okay, so this attack is independent of any model, protocol, cryptography that you use because the notion that if two devices communicate that they are indeed in their close proximities is simply wrong. It's simply incorrect. So that's the first test that we did was over a cable. So this is how our antenna looked like. The antenna that was close to the key. This is the antenna that we use. It's a Texas Instruments antenna that you can just buy for 20, 30 Swiss francs. It was this large because we wanted to increase the distance to the key. Of course, you don't want to get too close to the owner, right? So if you use a larger antenna and a stronger signal, you will excite the key and you will enable communication. Here on the side of the car, there's no need to use a very large antenna. So we just built our own little loop antenna, and we were able to excite the car and therefore to open the door. Then we said, well, pulling cables all around is a little bit cumbersome, so you don't want to be running around with cables. Let's build a wireless setup to do this. So it took us around 1,000 Swiss francs. What we did is we simply captured the signal from the car. We upmixed the signal to an intermediate frequency of 2.5 gigahertz. The choice is arbitrary. You can play with whichever frequency you like. We then relayed this up to 50 meters, but you can relay it up to as many meters as you like. It was captured on the other end of the antenna. It was downmixed to 130 kilohertz, and then we would talk to the key. The beauty about this setup is that we didn't actually decode the information from the wireless signals. We just upmixed it and downmixed it, which means that we didn't lose any processing in loops. So our entire setup here introduces a delay of about 20 nanoseconds. Why is this important? This means that our setup, so both of these upmixing and downmixing processes, will take only 20 nanoseconds. So all the other time will be just due to the distance. I'll tell you why this is very important later on. So this is which means that we can now build two receivers, two transceivers, one is small and the other one equally small, and one attacker has one, the other one has the other one, and we can come close to the key and close to the car, and we can unlock and start the car and leave. And if you bought a Bentley for 200,000 Swiss francs, this really can help you. So this is one of our prototypes that we played with here. I don't want to go into too many details, but here the signal was captured, and we are now building much leaner setups, but I don't have the pictures yet. Yeah. So this was here. So we captured the signals. Here we did the up conversion to 2.5 gigahertz. Here we captured the signal again. We did the down conversion, and that's it. And we established the relay. So then the fun part. Then we started analyzing how this works. The first victim car was my home car. Of course, the attack worked. It worked like a charm. So we took 10 models from 8 different manufacturers. None of these, as we observed later on, none of these models use the same protocols, even from the same manufacturer. But for us, it doesn't even matter. Whatever crypto you use, whatever messages you come up with, whatever authentication process it is, it doesn't help you because we are just forwarding messages from from the car to the key and back. So some of them use longer messages, probably a bit stronger crypto, longer keys, longer messages, and so on. Yeah. So these were our results. So we did initial tests, relay over cable versus model. So for some models, we didn't need any amplification. So if you look at M1 to M9, these are different models. We didn't need any amplification, and we could already relay up to 16 meters. There's no reason why you wouldn't amplify your signals. So this was done over the cable here, for example. So there's no reason why you shouldn't amplify. But the attack is very simple to do over 60 meters without any amplifier. So just to take two antennas, you pull a cable between them. Now 60 meters, this corresponds really to a parking lot scenario where you can put one of the antennas close to the exit, close to the payment terminal, and then you walk around with another antenna close to the car that you want. No one will probably notice some cables which are glued to the wall in a parking lot. So this is already in itself a problem, let alone when we build a wireless setup. Now, key to the antenna distance, this is also interesting. So if you're an attacker, you want to know how close you need to get to your victim. So here you see different, so this is the key to the antenna distance here, right? So this is to open the car here. So this is to open the door of the car. For some models with amplification, we managed to go up to 8 meters. But even with the best models with amplification, we managed to get up to 2.5 meters. So 2.5 meters is really not suspicious when someone gets to you, gets close to you within 2.5 meters distance. This distance here. So in the worst case, so in the best case for you, your car will allow a relay attack if someone is 2.5 meters away. And you know, this is not optimized at all. So the amplification that we used and the components we used, if you optimize them with the antenna gains that you set, that you have, you could push these even further. So I would see these as optimistic for the car manufacturers. Now, in terms of the in order to start the car, key to antenna distance was here. It was in this range as well. Okay. So the question that we asked ourselves was, how many delay is actually accepted by the car? The car must have some sort of a timeout mechanism. So if the car challenges you with a random bounce, the key is supposed to reply within certain time. So we wanted to test how much time this is. So how much of a timeout the cars allow. Why is this important? Well, this is important because if you would know how much time this is, we would know how long our relay could be. Okay? So possibly even you could imagine that if this timeout is long enough, you could relay over the internet. So you could steal someone's car if he's in Europe and his car is in the US. So that would be something that you could do if this time is long enough. So let's see. So how did we test it? So we used the software-defined radio, where we build different setups. So we actually used the software-defined radio FPGA to add tunable delays. So our minimal delay that we could test for was 5 microseconds, and we went from 5 microseconds to 10 milliseconds. So what were the maximum accepted delays by these different models? So this is in milliseconds. So the best model is 0.5 milliseconds, and the worst model is 10 milliseconds. Okay. So sorry, the best model is 35 microseconds. Now this is the best model. So 35 microseconds. This corresponds with the time of flight, which is propagation of the speed of light, right, to 5 kilometers. So in the best model, if the timeout is 35 microseconds, we could do a relay for 5 kilometers. For 10 milliseconds, we could do 1,500 kilometers. So even if you travel to, I don't know, Sweden, you could do this kind of relay. So this only shows that these timeouts are critical, but they're still quite long, right? 5 kilometers. And if you are in your office and your car is in a parking lot, this works like a charm. There's ample time actually, even in some of these systems. So in this system here, there's ample timing to decode the messages and to have the bits and then to demodulate the messages and then to do the modulation again. Yeah. So with some of these models, like this one, this non-physical relay will therefore be difficult. So the demodulation process will be difficult. But we didn't need that. We used a purely physical layer relay, And as I said, our setup introduced 20 nanoseconds of delay, which means that none of these systems could easily detect the 20 nanoseconds. So as I said, we did a relay on the parking lot. We did a relay when the keys were in the locked house and the car was parked in front of the house. I can tell you that this family now keeps their keys somewhere in the inner part of the house. They don't have this, they don't put them close to the door anymore. Yeah, this is an additional insight. So there's no, so besides starting the car when it can be empty and you are able to drive it away without maintaining the relay, there is also no trace of entry and start. Your key was used to open the car. Your key was used to start the car. So even if the car would be logging how many times it opened, which key was used to open the car, everything would look perfectly legit. And for legal and insurance reasons, this is a nightmare. So after we published this work, not only that we were talking to car manufacturers, but a lot with insurance companies. And they don't want to insure these cars. I mean, they have higher premium now being introduced for these kind of cars. And these are, you pay more for this system. And then your insurance premium increases. Which shouldn't happen that way, I guess. Okay. So, what are the immediate protection mechanisms? Well, if you have one of these, and if you're really paranoid, which even despite working for years in security, I'm not that paranoid, you can actually shield your key. There are very nice aluminum pouches, that you can use. So put your key in an aluminum pouch, and every time that you want to open your car, you could remove the key from the pouch. But of course, this removes convenience, right? You wanted to keep your key in your pocket. You don't want to, opening an aluminum pouch and taking it out every time that you want to unlock your car. You can also remove the battery. Now going back to that passive mode of operation, right? You remove the battery, and now you will significantly reduce the range of an active RFID tag. You will reduce it to a passive RFID tag, which means that then the attacker would really need to get really close to your, rub off you in order to get the signal out of your key. So, but of course, these seriously reduce the convenience of use. So there's no nice solution to it. There's no quick fix to this, except drawing this part out, and I open this like this. So drawing this part out, keeping it at home, and using the metallic key, which doesn't even look nice if you have such a system. So that's not a solution either. So all of these are not very convenient and are not very nice. So what we want to do in the long term, and this is a part of the research that my group does, we want to build a system that securely verifies proximity. So going back to the point of if two devices can communicate, that the implication is that they are actually close. Now in an adversarial setting, this doesn't hold. We need mechanisms that will be able to securely verify proximity. So one of those works is something that we recently did, and where we rely on protocols called distance bounding protocols, which enable two devices to securely verify their proximity based on the measurements of the time of flight. And I guess by now you also intuitively figured out that this is the only way to go, right? That if I want to verify that you are close, I have to send you a message. You have to do some processing on that message, send it back to me. I have to measure the propagation time, which will be in a few nanoseconds, and then I'm sure that you are close if you reply within a few nanoseconds. There are many challenges to be met there, because of course the processing on a key is some sort of a crypto operation, so it needs to be pretty stable, and it will take microseconds, right? But it needs to be stable within picoseconds or nanoseconds in order to be able to accurately measure the distance. And this is what we are currently able to do. So if you don't believe that this is feasible to measure nanosecond signals and so on, I can tell you that it is. It's doable. And with different types of ranging technologies like ultra-wideband and similar technologies, you can actually achieve quite accurate distance measurements. And with distance bounding protocols, you can have quite high level of, you can have secure proximity verification with component systems. Yeah, so this is a no-brainer essentially. So this is a really simple concept. You pull a piece of cable, it's a relay attack, and relays, especially at the physical layer, are extremely fast and efficient and actually very, very inexpensive. You don't need very expensive equipment to build this. This was all built with a very low budget, with few components that you buy online, and that's about it. So, just to stay for a minute, given that we have some time, on relay attacks. Relay attacks were recently also demonstrated on NFC communication. So now the new hype is NFC, right? All the phones should have NFC. We should do payments with NFC. NFC is the old way. Let's do NFC. It's also vulnerable to relay attacks. If you have your credit card in your pocket, which is NFC enabled, I will come to that, close to that card. Maybe half a meter is the distance that we can achieve in our lab easily. So within half a meter of you, I'll come with my antenna. I will excite your card, and the other antenna will be close to some payment terminal, and your card will be used to pay for my transaction. Now, of course, the credit card companies are saying yes, but we'll put a cap on how much money you can spend with this mechanism, so it will be up to 40 Swiss francs. Yes, it will be up to 40 Swiss francs, but how many times? I mean, how many transactions can you do in that? So, so we need techniques to perform secure distance measurement. We need them on a budget. We need them with some passive devices. So there are many challenges there, and we are currently working on that. So yeah, we have still almost 8 minutes for questions and discussion. So I welcome any questions or discussion.
For this attack to work for a long distance, you need to relay or amplify the UHF patch channel. Did you implement this as well?
Yes, yes, we did. I mean, that's even easier, right? Because that's a long range. That's radiated coupling. I mean, that's easy, right? There's no challenge there because this signal already goes up to hundreds of meters, so relaying it further wasn't that bad. So this back channel, I mean, there are many, and this was only a prototype. You could pick your frequency and work on that frequency, upmix, downmix, whatever makes you happy or gives you the range that you require, right? Yeah.
What if the queue charged the card in advance, and because the card will be much quicker, I think it has more calculation power to the card. The timing will be less critical to measure the distance. And so if you could make the gap even closer for this initial key card, and only within 1 2 seconds afterwards the card will open the key.
So I mean that will not help because here the card is the entity that measures the delay, right? That measures the time.
Yes, but the key could also measure the distance first. And only
how does the key measure the distance? I mean, the key challenges the car, and then the car replies.
Yes, and then the key could find out if the timing is close enough so that the key would afterwards.
But it doesn't matter if the car finds out or if the key finds out.
Yes.
The attack still works.
It's a logic, yes, of course, but one of the problem is that the key needs time to calculate the response. And
no, even if the key would respond. Okay, so even if in order for this to work, in order for a solution for this to work, it would require that the key processes in constant time, not necessarily in zero time. It could process in microseconds, but the standard deviation of that processing should be very small, so in picoseconds or in nanoseconds, right? So this would be, and then the car in turn would have to measure precisely in nanoseconds the round trip time of the challenge, and then reply minus the processing of the key, right? And that would be the only solution. I mean, with the currently deployed systems, if the key would start, it wouldn't help. Unless the owner actually presses the button, right? And you can imagine even if you would try to deploy such a solution where the key would start, this would mean that the key would be transmitting and the key would become more complex and larger and it would require more power. And implementing that the key measured the distance precisely, that's
but if the car measures the key, the attacker could, normally could not make the delay longer to get into this standard duration delay.
I mean the delay. So the best sort of detection that the car manufacturers did is 35 microseconds. Okay, this is how much the car weighs. Now there are also, I mean, here it's not only these are not only the hardware requirements of these systems, but this is also the convenience of use here, right? You can't have your, if you're, so when you come close to the car, you will grab a handle and the car should open, should click and open. If you grab a handle and your car doesn't open, and then you have to grab it again and it doesn't open, and it opens 1 out of 3 times, you'll go back to the shop and you give your car back. So there is also a lot of such delay. I mean, a part of this is such delay, right? Convenience of use plays a role here. And also, what plays a role is that they probably didn't want this system to be too expensive to measure the distance in round trip times and so on. So they, when we talk to the car manufacturers, they sort of had in the back of their minds that these kind of attacks might be feasible, but they were hoping that no one's going to exploit this and that this will not be a problem. But today, if you have software-defined radios, a bit of electronics knowledge, you can pull up this kind of stuff. Yes?
How complex can you make the distance measuring systems? Because if you have too much calculation, I believe the calculation will compromise the distance again.
Yes. So this is what. So this is exactly one of the things that we have been working on, and what we have currently, we have a setup that allows. So we have a receiver, which in this case you can see as a key, right? Which will receive a message. So this is your wireless signal, right? Then we'll process this message and we'll send out a reply. Now this reply will be a function of this challenge. So this is some sort of announce. This will be a function of announce, and this function of announce will come out, and this processing here will be below 1 nanosecond. So we have a prototype that does this, that receives a signal on the wireless channel, processes something within less than 1 nanosecond and sends it out. But again, why are we able to do this? Because we are doing everything now. There's no demodulation, there's no, we don't have any preambles here, there's no synchronization and so on. So all the intelligence or the logic is at the side of the car. And then you can make, so if you sort of flip the complexity from here to here, if you do everything now here, you will do a bit more processing here, but this will become very fast and very stable.
Wouldn't it be easy to reconstruct this divide on the right side then, and to carry it, to carry a second device into the relay again?
You can't do a relay attack on this kind of a system. Why? Because the car will then time out. So your timeout will be about 10 nanoseconds, which corresponds roughly to 1.5 meters. I mean, it's essentially 30 centimeters divided by 2, and then 33 meters divided by 2. Okay, around that. We have 30 seconds for another question. Yes?
Have you already seen someone abusing it?
Yes, we have. So we were not able to confirm fully but we found on a black market you can buy for 40,000 Swiss francs a kit that seems to be doing this kind of thing. You can buy it from Bulgaria. 40,000 Swiss francs. I mean, we are a university, right? I mean, I would find it very difficult to sign for such an expense. There was a, maybe we can take it.
What about measuring speed of then you don't have this approach.
How do you identify the owner?
Yeah, so this is called a text key at first and it's nothing.
So so you can make the relay as long as you want, as long as this allows you. So you can make it 5 kilometers up to 1,500 kilometers. So measuring somehow that the owner approaches the car or leaves the car.
Yeah, the cord text key for first time, and the owner usually walks in a certain speed.
What if it's owner or wife?
Yeah, it doesn't matter. Just like keep it close. If you do the relay attack, I don't think you have much time to walk there with the cable.
Sorry guys, I have to interrupt here because you can
We
probably
can take it
talk
offline.
later.
So, yeah, thanks.